What exactly defines a planet? It's a question that has fascinated astronomers and stargazers for centuries. Most would say it's a big ball of stuff orbiting a star, and that's mostly right. It's a celestial body, a world unto itself, bound by gravity and bathed in the light of a distant sun. But there's more to it than meets the eye, but the universe loves its fine print. The cosmos is a complex and nuanced place, and the definition of a planet is no exception. Officially, according to the International Astronomical Union, a planet must do three things to earn its title. These criteria are the gold standard for planethood. First, and perhaps most obviously, it must orbit a star, like our Sun, the radiant heart of our solar system. This orbital dance is what defines a planet's year, its journey around its stellar parent. Second, it must be massive enough for gravity to pull it into a nearly round shape. This is known as hydrostatic equilibrium, where gravity's relentless pull molds the planet into a sphere. That's why planets are spheres, not potatoes. The immense gravity ensures a smooth, rounded form, a testament to the power of cosmic forces. Third, and this is where things get interesting, it must have cleared its neighborhood, meaning it dominates its orbit, sweeping away smaller objects. It's the bully on the block, gravitationally pushing aside any cosmic debris in its path. This last rule is why Pluto lost its planet status, a decision that sparked debate and controversy among scientists and the public alike. It shares its space with many icy bodies in the Kuiper Belt. It simply couldn't clear its orbital path, failing the final test of planethood. So, a true planet is the gravitational king of its orbit. It reigns supreme, its gravity shaping the space around it. In our solar system, we have 8 such worlds, each with its own unique characteristics and mysteries. From Mercury, the scorching inner world, to Neptune, the icy giant at the edge of our solar system. But the universe is vast, an almost incomprehensible expanse of space and time. Our galaxy alone has hundreds of billions of stars, each a potential sun for countless other worlds, and most of those stars likely have planets of their own, exoplanets orbiting distant suns light years away. We now know the cosmos is teeming with worlds, far more than we ever imagined. Each new discovery expands our understanding of what a planet can be, challenging our preconceived notions and pushing the boundaries of our knowledge. The definition may seem strict, a rigid set of rules for classifying these celestial bodies, but it helps us make sense of the incredible diversity out there, the sheer variety of planets that populate the universe. Planets are everywhere, scattered across the cosmos like grains of sand on a beach, and we're just beginning to explore this cosmic ocean, to chart its depths and discover its hidden treasures. The more we learn, the more we realize how special and common planets really are, each a unique world with its own story to tell. Our journey through the solar system is just the start, a stepping stone to exploring the vast planetary landscape beyond. The universe is full of planetary surprises waiting to be found, new worlds that will challenge our understanding and inspire our imaginations. Planets, those celestial bodies that dot the cosmos, are not born overnight. They are carefully and meticulously forged. They arise from the leftovers of starbirth, the cosmic crumbs that remain after a star has ignited its nuclear furnace. It all starts in a giant, cold cloud of gas and dust, a nebula, a stellar nursery where stars and planets begin their lives. These nebulae are vast, sprawling regions of space, often spanning hundreds of light years. A disturbance, like a nearby supernova, the explosive death of a massive star, sends shockwaves rippling through the nebula. This cataclysmic event triggers the cloud to collapse and spin, drawn inward by its own gravity. The nebula begins to rotate faster and faster, like a cosmic ice skater pulling in their arms. As the cloud spins, it flattens into a protoplanetary disk, a swirling disk of gas and dust surrounding a nascent star. At the center, the pressure and temperature become so intense that nuclear fusion ignites, birthing a star. The leftover material, the gas and dust that didn't make it into the star, forms a swirling disk, the raw ingredients for planets. This disk is a dynamic environment with particles constantly colliding and interacting. Tiny dust grains, microscopic particles of rock and metal stick together through electrostatic forces. These grains grow into clumps, larger aggregates of matter held together by gravity and other forces. These clumps continue to accrete, growing into rocks, small rocky bodies orbiting the star. Then boulders, larger still, massive chunks of rock and metal hurtling through the protoplanetary disk. Over millions of years, this process continues, a slow and steady accumulation of matter. These collide and merge into planetesimals, planetary embryos, the building blocks of planets. The early solar system was a chaotic demolition derby, a cosmic arena where planetesimals clashed and collided. It was a time of intense bombardment, of these bodies smashing together, sometimes merging, sometimes shattering. Closer to the sun, where temperatures are high, only rock and metal survive the heat, preventing ices from forming. This leads to the formation of the small, dense, rocky planets like Mercury, Venus, Earth, and Mars. Farther out, beyond the frost line, the distance from the star where it's cold enough for volatile compounds to freeze, it's cold enough for ices to form, water ice, methane ice, and other frozen compounds. This abundance of icy material allows planetesimals to grow much larger, accumulating mass more quickly. These massive cores attract, with their immense gravitational pull, hydrogen and helium, the lightest and most abundant elements in the universe. This leads to them ballooning into gas giants like Jupiter and Saturn, massive planets composed primarily of hydrogen and helium. The architecture of our solar system, the arrangement of planets around our star, rocky worlds inside, close to the sun, giants outside, farther away in the colder regions, was set by these early conditions, by the temperature gradient and the availability of different materials in the protoplanetary disk. Every planet, from Mercury to Neptune, each with its own unique characteristics and history, began as dust in a cosmic disk, a testament to the power of accretion and gravity. The process is messy, violent, and beautiful, a cosmic dance of creation and destruction. And it's happening right now, this very moment, around countless young stars across the galaxy, in stellar nurseries teeming with potential. Planet formation is the universe's ultimate recipe for worlds, a process that has shaped countless planetary systems and continues to unfold across the cosmos. The inner solar system is home to the rocky or terrestrial planets, Mercury, Venus, Earth, and Mars. Built from heavy elements like iron and silicon, these worlds are dense, solid, and small. They formed close to the sun, where only metals and rocks could survive the heat. Each planet tells a different story. Venus is a greenhouse inferno, Mars a frozen desert, Mercury a scorched remnant, and Earth the only known oasis for life. Their surfaces are scarred by impacts, volcanoes, and shifting crusts. Studying them reveals the possible pasts and futures of our own world. They're siblings, shaped by their place in the solar system, and a bit of cosmic luck. The rocky planets are laboratories for understanding planetary evolution. Each one is a chapter in the story of our solar system's inner sanctum. Mercury, the innermost planet in our solar system, closest to the sun, a mere 58 million kilometers away. It is a world of extremes, a stark reminder of the power of proximity to a star. During its scorching days, the surface temperature can soar to a staggering 430 degrees Celsius. But as darkness falls, the temperature plummets to a bone-chilling -180 degrees Celsius during its freezing nights. At its heart lies a massive iron core, making up a significant portion of the planet's mass. Its thin, silicate crust, marked by towering scarps and ridges, suggests a violent past, a history etched in stone. Scientists believe that this crust was likely stripped away by a colossal impact early in its formation. Mercury is a battered survivor, a testament to the harsh realities of the early solar system, dense and scarred, a world forged in fire. Next we turn to Venus, often called Earth's so-called twin due to its similar size and composition. But beneath the surface, Venus is anything but friendly, a world transformed into a hellish landscape. Its thick, toxic atmosphere, composed primarily of carbon dioxide, creates a runaway greenhouse effect, trapping heat with terrifying efficiency. This makes it the hottest planet in our solar system, even hotter than Mercury, despite being further from the sun. Ominous clouds of sulfuric acid perpetually shroud the surface, obscuring any view of the landscape below, and the atmospheric pressure is crushing, equivalent to being nearly a kilometer beneath the ocean on Earth. Adding to its bizarre nature, Venus spins backward and incredibly slowly on its axis. This slow rotation means that its day is longer than its year, a truly perplexing phenomenon. It's a world where climate disaster reigns supreme, a cautionary tale of a planet that took a drastically different path than our own. Venus serves as a stark warning, a reminder that proximity and size are not enough to guarantee a habitable world, not a twin, but a cautionary tale. Both Mercury and Venus, in their own unique ways, show us the extremes of planetary evolution, the diverse paths that worlds can take. Their stories are cautionary tales etched in scorching heat and toxic clouds, lessons from worlds gone astray. They highlight what can happen when planetary conditions spiral out of control, when the delicate balance is irrevocably disrupted. These worlds remind us, with their extreme temperatures and hostile atmospheres, just how delicate the balance for habitability can be, a balance we must strive to understand and protect. In the vast expanse of the solar system, even neighbors, born from the same cosmic dust, can be radically different, each following its own unique destiny. Earth is unique, teeming with life, covered in water, and protected by a dynamic atmosphere and magnetic field. Plate tectonics and climate cycles keep our planet habitable. Next door, Mars is a cold, rusty desert. Once it had rivers and lakes, but lost its atmosphere and water over time. The likely culprit, the loss of its magnetic field, leaving it exposed to the solar wind. Now water is locked as ice, and Mars is a fossilized world. Earth and Mars are planetary siblings with diverging destinies. Studying Mars helps us understand the fragility of habitability. Our planet thrives while Mars is a ghost of what might have been. The contrast is a powerful lesson in planetary evolution. Beyond Mars lies the asteroid belt, the boundary between rocky worlds and gas giants. The inner planets are small, dense, and solid, built from rock and metal. Beyond the frost line, Jupiter and Saturn formed from ices and gases, growing massive enough to capture hydrogen and helium. These gas giants are immense, low density, and lack solid surfaces. Farther out, Uranus and Neptune are ice giants, hybrids with thick atmospheres and icy interiors. The split between rocky gas and ice giants defines our solar system's structure. It's all about where and how planets formed in the early disk. This architecture is likely common across the galaxy. The diversity of planets is a direct result of their birthplaces. Our solar system is a blueprint for planetary systems everywhere. Jupiter is the king, more massive than all other planets combined. Made mostly of hydrogen and helium, it's a failed star that never ignited. Its storms, like the Great Red Spot, are legendary. Jupiter's moons are worlds of their own. Io is volcanic, Europa may hide an ocean. Saturn, the jewel of the solar system, is famous for its stunning rings. These icy rings are thin, delicate, and mesmerizing. Saturn is less dense than water and has fierce winds. Its moon Titan has lakes of methane, while Enceladus sprays water from a hidden ocean. Both giants have vast families of moons, each with unique stories. Jupiter and Saturn are miniature solar systems, shaping the outer solar system. Their gravity influences everything from asteroids to comets. They are the architects of our planetary neighborhood. Uranus, tilted on its side, rolls around the sun in a bizarre orbit. Its blue-green color comes from methane, and its seasons last decades. Uranus is a quiet, icy world with faint rings and moons named after literary characters. Neptune, farther out, is deep blue and stormy, with the fastest winds in the solar system. It was discovered by math before it was seen. Neptune's largest moon, Triton, orbits backward and erupts nitrogen geysers. Both ice giants are mysterious, dynamic, and cold. Their unique features challenge our understanding of planetary science. The outer solar system is a realm of extremes and surprises. Uranus and Neptune are the enigmatic sentinels at the edge of our planetary family. For centuries, we knew only our solar system's planets. Now, we've found thousands of exoplanets, planets orbiting other stars. They come in wild varieties: hot Jupiters, super-Earths, and worlds with diamond or glass rain. Some orbit two stars, others have bizarre orbits. Each discovery challenges our theories and expands our view of what's possible. Studying exoplanets helps us understand how planets form and why our solar system is arranged as it is. The ultimate question: are we alone? By searching for biosignatures on distant worlds, we may soon find hints of life elsewhere. Planets are more than cosmic objects, they're potential homes for life. The universe is a vast laboratory, and every planet is a new experiment. Our exploration has just begun.